Our wanted quantity here is the molecular formula. To determine the molecular formula, we need to know the molar mass of the molecular formula, which is given in the problem, as well as the empirical formula, which is not given in the problem. Womp womp. But we do have some information on the atoms present in the compound, and that information is in a format that would allow us to get to moles. So we can determine the molecular formula of this compound. Notice that the setup here will be slightly different than the setup of the empirical formula problems that we have already completed because we are given values in terms of grams and not in terms of percentages. This isn't a big deal, and if anything, it's slightly easier as we don't have to make the assumption about the size of the sample. We can just move straight from these gram values to our moles values. Here I have completed the conversion from grams to moles for all three elements in our compound. Moving from grams to moles of each element gets us closer, but we need to move from these fractional values that have decimal places to whole number values. So we need to divide all three of these values by the smallest among them. Note that the moles of carbon and the moles of oxygen are essentially equal right now, so this division step really gives us two 1 values right away. Remember that what you do to one part of your equation, you have to do to all of it. So you also have to divide moles of hydrogen by the smallest value, which also gives you a whole number. All of our molar values are right now in terms of the smallest whole number ratio, so we can move our data into an empirical formula. Knowing the empirical formula allows us to calculate the empirical formula's molar mass, which is 30 grams per mole. At this point, we need to compare our molecular formula to our empirical formula. We know two things. One, that the two formulas overlap in what atoms are contained and in what ratio those atoms are present, and two, the molar masses of both of our formulas. The last pieces of information are extremely useful as we can compare the molar mass of the molecular formula to the molar mass of the empirical formula through a simple division. The value 2 here is telling you that the molecular formula's molar mass is twice as big as the empirical formula's molar mass. This then translates to the atom count for the molecular formula being twice as big as the atom count for the empirical formula. The empirical and molecular formulas will always keep the same ratio of atoms, as the molecular formula is just a multiple of our empirical formula. So, if we know that the empirical formula is CH2O, then an atom count twice as big would just involve multiplying all of the subscripts by 2, which would result in a molecular formula of C2H4O2. This particular molecular formula happened to have a molar mass of 60 grams per mole, but know that there could be a molecular formula with a molar mass of 90 grams per mole, which would result in your tripling the subscripts in the empirical formula. And there's probably a molecular formula with a molar mass of 120 grams per mole, which would result in quadrupling the subscripts in the empirical formula, and so on.